Okay, so we were looking at the second derivative test and maximum and minima, finding absolute max and min. It's just like before, but in Calc 1. That is, you check local max and min, and then you check any endpoint or boundary constraint. And so the last problem we were looking at was this problem. And we were able to find 0, 0. And then we found the point where we took those two together and we got x equals 1/3 and y equals 1/3. Okay, and so then we have this last value that we need to solve for. And that is the case. So now we have the point 1/3, 1/3. So that was another set of, oh, I forgot my parentheses. Another set of points. And then we also have to check what happens if x is not 0. Okay, so I'm sorry, that's not what I want to say. So we already know that the point 0, 0 will work, but if x is 0, it knocks out this whole second equation, but it can still give us something else in the top equation. So if we take these equations, we have y times 1 minus 2x minus y is equal to 0, and x times 1 minus 2y minus x is equal to 0. And if x is equal to 0, then the second equation is automatically satisfied. But let's look at the first equation. If x is equal to 0, y can be 0, or we already got y can be 0, or 1 minus 2 times x minus y can be 0. So that says 1 minus y can be 0, or y can equal 1. So we get the point 0, 1 out of there. And then in the second thing, if y is equal to 0, clearly the first equation is satisfied. So x could also equal 0, or 1 minus 2 times y minus x could equal 0, which says 1 minus x equals 0, or x is equal to 1. So we also get the point 1, 0. So now all the points that we can possibly get as critical points are found. 0, 0, 1/3, 1/3, 0, 1, and 1, 0. Okay, so those are our possibilities. And when we go and check these, we get the volume. So let's go back. This was checking the volume of a box. We were maximizing it. And the function that we were maximizing the volume was x times y times 1 minus x minus y. So the volume at xy was x times y times 1 minus x minus y. So therefore, v at 0, 0 is v at 0, 1 is v at 1, 0. All of those are 0. So all of those are minima. Okay. The only one that's not is v at 1/3, 1/3 is 1/3 times 1/3 times 1 minus 1/3 minus 1/3. But that turns out to be 1/3 cubed. So that's 1/27. And that's what we get. Okay, I wanted to do another problem. Which problem did I want to do? Nope, not that one. This one. Okay. So what is the shortest distance from that surface to the origin? Okay, so how do we do that? All right, so here's the origin. Right here. And there's some surface. Who knows what the surface looks like that's floating over top? There's some surface floating over top here. Okay, this is the surface. And we want to find the shortest distance from the surface to the point, so to the origin. So there's some point on the surface. And the point on the surface is X, Y, Z. And we want to find the shortest distance from that point to the origin. Okay, so now in order to find the distance, we need the distance formula. So we need the distance from the point P being X, Y, Z to the origin being 0, 0, 0. So the distance formula is the square root of X minus 0 squared plus Y minus 0 squared plus Z minus 0 squared. Okay, so that's the distance. Now, as a rule of thumb, we never minimize distance. We always minimize distance squared. It is so much easier to minimize distance squared. Okay, so we will minimize distance squared. So F of X, Y, Z is going to be X squared plus Y squared plus Z squared. Okay, so we want to minimize this function, minimize this function subject to the fact that the point XYZ is on the curve. So therefore the point has to satisfy X times Y plus 15X plus Z squared is equal to 204. So here is the function we're trying to minimize, and here is our constraint. So you need to always be able to identify the function you're trying to minimize or maximize and your constraint. So for us, the points have to be on this curve. So that's what makes that the constraint. Okay. So now again, we can't minimize or maximize a function of 3 variables. So I need to eliminate one of these variables. What is the most logical one to eliminate, Anaya?
Y. No.
Y.
Z.
Z, because that's easy. Here's Z squared and here's Z squared. Okay, so I would have to solve for X over here. That's hard. I'd have to solve for Y over here. That's hard. It's better just solve for Z. So when we solve for Z, you get Z squared is 204 minus XY minus 15X. So now I'm going to put that into my function. So now I'm going to minimize f of xy being x squared plus y squared plus 204 minus xy minus 15x. Okay. Since I know z squared always satisfies that equation, I just plop it in there. All right, so therefore, I'm going to now find the partial of f with respect to x and the partial of f with respect to y. So what do you get? What's the partial of f with respect to x?
Sorry. 2x
All right, 2x
minus y minus 15. And then the y one is 2y minus x.
Okay. All right. So therefore, they both have to be set equal to 0. And when you set them equal to 0, you end up getting here from this equation, I get x is 2y. So therefore, when I plug it into this equation, I get 2 times x, which is 2y, minus y minus 15 is equal to 0, or 3y is equal to 15, or y is equal to 5. And then if y is equal to 5, then I get x is equal to 10. Okay. So therefore, z squared is equal to 204 minus x times y, so that's 50, minus 15 minus 15 times x, which is 10. So I get z squared is equal to 204 minus 50 minus 150. So z squared is equal to 4. So therefore, the maximum of the function is x squared, which is 100, plus y squared, which is 25, plus z squared is 4. So that's 129. But now we just have to remember that the function we were trying to maximize was the square root of that. So our answer is the square root of 129. Okay. Any questions about that?
No.
Okay. All right. All right. Here's one more. This one is find the volume of the largest rectangular parallelepiped that can be inscribed in the ellipsoid 36 x squared plus 9y squared plus 4z squared is equal to 36. If the edges are parallel to the coordinate axes. Okay. Okay, 36x squared plus 9y squared plus 4z squared equals 36, okay? All right, so we are trying to maximize volume of a parallelepiped. So now this is a kind of weird one. Let me try to draw it for you. So here's what we have. We have a parallelepiped. We have an ellipsoid first. So let's draw the ellipsoid. So I have an ellipse that looks like this. And then I have an ellipse that looks like this. Okay, so there's the ellipsoid. All right, it actually comes down like this. Okay, so there's the ellipsoid. And I want to put in it a box. Okay, so I'm trying to put in this thing a box that looks a parallelepiped. So it's a square box that looks like this. Inside this thing. And it goes back and, you know, I'm trying to put this box inside of here. Okay. And I know that the volume of the box, well, let's think about the volume of the box. So it'll go out X and back X. So the volume is going to be 2X times 2Y times 2Z. All right. So the volume of the box is 8XYZ. All right. Oh no, the edges are parallel to the coordinate axis, so I don't have to do twice as big. I'm not doing it twice as big. I'm only doing, it's only backed up against the origin. So it's just going X, Y, Z. And then the corner edge of this box is on the ellipsoid. So the constraint is that the corner edge the corner edge is 3x 36x squared plus 9y squared plus 4z squared is 36. Okay, and so we are trying to find the largest. So that says we want to maximize volume. Subject to. So we're trying to maximize the volume subject to the constraint of that. Okay, so now this is a problem kind of similar to the last one, except this one is not nearly as nice. And the reason why it's not nearly as nice is because you can see that it's going to be hard to solve for X, Y, or Z. So it's difficult. It's not hard. It's just ugly to solve for X, Y, or Z. Doesn't matter which one you pick, I'm going to choose Z. So if I get 4Z squared, 36 minus 36x squared minus 9y squared. So I get Z squared is going to be 36 minus 36x squared minus 9y squared over 4. So Z is 1/2 the square root, or 1/2. I'm not even gonna write it, I'm gonna write it like that. 36 minus 36x squared minus 9y squared to the 1/2 power. Not cute. So now I want to maximize my function f of xy, which is going to be v of xy now. That's x times y times 1/2 36 minus 36 x squared minus 9y squared to the 1/2 power. Okay. So I think I might have done something wrong. No, I didn't. Yeah. Oh, I know what I did. I know what I did. Let me see here. I did something different when I solved this before. I think I divided everything by 36 first. It made it easier. So let me go back and do that. That made it easier. So then I ended up with Z squared over it does not matter. I'm going to leave it just like it is. Okay, I'm going to leave it just like it is. I can factor out the 36. So if I factor out the 36, the square root of 36 is 6. When I pull that out, that pulls out a 6. So I get 3xy. And now I get 1 minus x squared minus y squared over 4. Because I divided everything through by 36. So that becomes y squared over 4, as I said. That becomes 1. Pull the 36 out, it comes out as the square root of 6 multiplied by 1/2, I get 3. Okay, I'm happy with that. Okay. All right, so now I need the partial of f with respect to x. And what does that turn out to be? Oh boy, well, we have 3y. And so I'm going to get the first, which is x, times the derivative of the second, which is 1/2 times 1 minus x squared minus y squared over 4 to the negative 1/2 power times a negative 2x plus the second, which is 1 minus x squared minus y squared over 4 to the 1/2 power times the derivative of the first, which is just 1. Okay, so this turns out to be 3y. And then I'm going to, I'm going to factor out 1 minus x squared minus y squared over 4 to the negative 1/2 power. In the second piece, I get a 1. And in the first piece, I get 1 minus x squared, I believe. 1 minus 1/2 and a 2, so I get 1 minus x squared. Okay. Then I take the partial of f with respect to y. So now I'm going to pull out 3x. And I'm going to get y times 1/2 times 1 minus x squared to the minus y squared over 4 to the negative 1/2 power times minus 1/2 y, because that's the derivative of what's inside, plus the second, which is 1 minus x squared minus y squared over 4 to the positive 1/2 power times the derivative of the first. So that equals 3x times 1 minus x squared minus y squared over 4 to the negative 1/2 power. And now I'm going to get 1 minus 1/4 y squared. Okay. We set that equal to 0. Okay. All right, so the numerator, I'm sorry, the first equation, if y is equal to 0, and in the second equation, y is equal to 0, y is equal to 0, then x would have to be 0. But in this first equation, if y is not equal to 0, then x has to be plus or minus 1, or x equals 1. Now, if x is 1 and y is not 0, then y has to be 2. Okay. And as you can see, my intent was not to finish this problem. And the reason why is because this problem is very messy. So there is a much nicer technique that we can use to solve this problem, and it is called Lagrange multipliers. All right. So let's look at this section. on Lagrange multipliers. So our learning objectives are to be able to solve optimization problems that have 1 and 2 constraints using the method of Lagrange multipliers. All right, let me see, that is the last. Wow, girl, we winding down. We have one more module. Okay. All right, this is what we're doing. Again, same thing. We have an optimization problem with constraints. All right, so we want to maximize or minimize f of x, y, subject to g of x, y is equal to a constant. All right, so the way we're going to look at this is we need to find the point x naught, y naught that we're looking for. We need to find x naught, y naught is on C, which is a level curve of the function g of x, y. All right, so now if you remember, we have a three-dimensional shape. So let's say we have something that looks like this. And I have okay, and I have a level curve so this is a level curve. And we say that, remember that the gradient of f, all right, is the function changes, the directional derivative is the highest, is the largest when it moves in the direction of the gradient. Okay, so now, so we will have this is a level curve. So now if x naught maximizes or minimizes f of x on a curve C, then the gradient of f, all right, which is x naught, y naught, is perpendicular to the curve at the point x naught, y naught. All right. So here I have And this is the gradient of f. Okay. So now the gradient of g, all right, is perpendicular to the curve at the point x naught, y naught. That means the gradients are parallel. Now, two vectors that are in the same direction, that means they're parallel, so they're in the same direction. The only thing that can be different is their magnitude. So that means one must be a multiple of the other. So if one is a multiple of the other, that means there exists a number lambda such that the gradient of f at the point x naught, y naught is equal to a constant times the gradient of g at the point x naught, y naught. And this lambda is called the Lagrange multiplier. Okay. So I'm going to go back and solve that problem using a Lagrange multiplier. All right, so let's see. The problem was, it wasn't cute. Find the volume of the largest rectangular parallel pipette. Okay. So here's the problem. All righty. All right, so we are trying to maximize volume. And the volume was X, Y, Z. So that's going to be my F. It's just the product of them. And my constraint was that 36x squared plus 9y squared plus 4z squared equals 36. So that looks like to me g of x, y, z is 36x squared plus 9y squared plus 4z, and that is equal to 36. So this is g of x, y, z is a constant. So it's set up just like I need it to be. That is, I want to maximize a function. This one happens to be a function of 3 variables. Maybe I should have done one of 2 variables first, but I was gung-ho to solve the one we just got finished with. And so I'm not going to solve this one. I'm going to wait. I want to solve a function of 2 variables first, because a function of 2 variables will be easier. Okay, so we'll come back to that. But this is exactly the setup that I could use for Lagrange multiplier. So let's just do a function of two variables first. Okay, so we want to find the relative extrema of the function f of xy is equal to 3x plus 4y minus 3 if the point xy lies on the circle x minus 1 squared plus y squared is equal to 25. Okay, so this one is x minus 1 squared plus y squared is equal to 25. Okay, so we are now trying to maximize and minimize f of xy. The function is f of xy equals 3x plus 4y minus 3, and the constraint is g of xy is equal to 25, where g of xy is x minus 1 squared plus y squared. Okay, so now we need to find the gradient of f. So the gradient of f is the partial of f with respect to x, the partial of f with respect to y. And the gradient of g is the partial of g with respect to x, the partial of g with respect to y. All right, so what is f sub x? Fx is 3 and fy is 4. G sub x is equal to 2 times x minus 1, and g sub y is 2y. All right, so now I need the gradient of f to equal lambda times the gradient of g. That means f sub x is equal to lambda times g sub x, and at the same time, f sub y is equal to lambda times g sub y. Okay, so that says 3 is equal to lambda times 2 times x minus 1. And my other equation is 4 is equal to lambda times 2y. Now here's the thing. Sometimes you will solve for lambda, sometimes you won't. This one, I think it's easiest if I solve for lambda. So in the first equation, I get lambda is equal to 3 over 2 times x minus 1. And in the second equation, I get lambda is equal to 2 over y. So therefore, both those things must be equal. So that says to me 3 over 2 times x minus 1 has to equal 2 over y. All righty. That says to me that y is equal to 4/3 times x minus 1. So now I have a relationship between x and y. And I'm going to put this into the constraint. So my constraint, if you remember, was x minus 1 squared plus y squared is 25. So now I get x minus 1 squared. Y squared is going to be 4/3 times x minus 1 squared is 25. So now I get x minus 1 squared plus 16/9 times x minus 1 squared is 25. So now I get (25) over 9, x minus 1 squared is equal to 25, or x minus 1 squared is equal to 9. So that says x minus 1 is plus or minus 3. So x is equal to 1 plus or minus 3. So x is equal to 1 plus 3, which is 4, or x is equal to 1 minus 3, which is -2. Okay, so how many possibilities do I have? Well, I already know, oh, we're over time. I'll see you tomorrow.
See you tomorrow.
All right, thanks, bye.